Okay, so I talk about more about the planet formation. I carry out the planet formation, planet population synthesis simulation for single stars, not binary, and to predict the distribution of the ejected planet during or after planet formation. To compare the predicted mass function with SUMETO. Okay, so let me start. Yeah, actually, I didn't do any plant population synthesis recently, but previously I was working on that and yeah, making some modeling each of the process and to combine and for given distribution with this product ideas, we can generate this kind of the distribution and try to explain the existing data or predict the unseen region planet and using the observation, we try to calculate a theory. But so far, most of the planet population synthesis is for the bound planet and not ejected. But actually, in a model, ejection process is already included. So I just try to pick up the data. So this model, this one is okay. Oh yeah. We assume the planetesimal accretion, but the ejection mechanism is the same for the pebble accretion. So the not so different. So for the growth and the migration model of gas giants, we follow the prediction in this paper. So actually, essentially, it is a Kanagawa et al.'s migration model. And the other process, like scattering, we use the very old models. So this is a final result of the predicted distribution for the bound planet. In this case, host stars is G dwarfs, so the solar type stars. So the final semi-galaxies and the mass of the planet and the rocky one, icy, and the gaseous one. And so in this calculation, actually there are many ejected planets. So I plotted here. Scale is a bit different, but don't worry, I just made a mistake. So this is a semi-axis before before ejection, and this is mass of planet. So actually, this is the some distribution of the ejected planet, but this one is before ejection. So in the case of the microlensing observation, so for this, we need to worry about the detection limit for radial velocity or transit or direct imaging. But these are ejected planets. So actually, there's almost no restriction, in this range. So maybe this is too small, but everybody can be observed. We also did similar calculation for M stars. But you find that the giant planets are very rare. It is consistent with radial velocity observation. But still some ejection occurs. But they're mostly icy giants. Icy planets. And up to 10 Earth mass or something like that. Because the host star's mass is low, then the potential is shallow, so that even the small guys, Earth mass size planet can eject other planets. But the population is not so big. So let me first show the final result. So we did this kind of simulation with the solar type star, 0.5 solar mass star, and the 0.25. Of course, so for the low mass stars, relatively small mass planets are ejected, but the absolute value is it's not so big. So still, we find that in particular in low low mass region, our prediction is much lower than the Smithson's prediction based on the observation. So let me explain in more detail what's this. So what's this peak and what's this peak? So in our model, there are two mechanisms for ejection. So this one, this orange one, this is due to the migration of the planet. When the planet migrate inward, there are many other planets inside. So there's, depending on the condition, the separated or ejected. I will explain in more detail. This is during the, I mean, it is in the gas disk because the planet migrate. Another process is, orbital instability after this gas depletion. So these are, so this contribution is this brown one. So in this case, it's if the giant planets are three or more, they part of each other. So due to the circular perturbation, eventually they start orbit crossing and one planet is ejected. So this distribution is ejected. Okay, so let me go back in more detail. So the gravitational perturbation. So for ejection, I want to point out that the close encounter is needed. In the case of circular perturbation, so there are distant encounters. Of course, a small perturbation pile up, accumulate. Then the eccentricity is excited. But this process is relatively slow, which means that the orbit averaging is available. So for this planet, this perturber is always orbit average. So this is equivalent to the potential to the eccentric ring. Because it is non-asymmetric, angular momentum is exchanged, so the orbital eccentricity is excited. But this potential is stationary, which means that the energy is conserved. So no ejection occurs only by this process. But for example, in mean motion resonance or circular resonance, usually they don't they don't eject the planet, but the eccentricity is more highly excited. So as a result, orbit crossing with other planet occurs, and then the cross encounter, ejection can be occurred. But anyway, so the cross encounters repeat until ejection, the collision, or orbit crossing with another planet. So Eve already pointed out that in this case, orbital eccentricity can be pumped up to the, not the eccentricity, later velocity dispersion can be pumped up to the perturbed surface escape velocity. So this value is equivalent to the orbital eccentricity. So if it is larger than unity, ejection occurs. So in a model, we assume the Rayleigh distribution for the excited eccentricity. So the kind of a Monte Carlo simulation we did. So for the shepherding and the ejection, we used our previous papers model. So when this is planet and it migrate inward, so the orbital distance becomes small. So the important point is orbital spacing scaled by Hugh radius of the migrating planet. So if there's a convergent migration, of course, the orbital distance becomes smaller. Also, if this is a gas giant, it accretes the gas and the runaway gas accretion, then the Hugh radius expand rapidly. Also in this case, orbital distance, scaled orbital distance decrease. On the other hand, for the when this distance becomes small, scattering occurs. In that case, scattering is mostly repulsive. So the pumped up eccentricity and the orbital distance expand. And after that, orbital eccentricity is damped by gas disk, like gravitationally or also the gas drag. And so the orbital scaled orbital separation increase. So this decrease and the increase compete. If the increase wins, then always these planets are just a shepherd, just a push inward, inward, inward. But otherwise, this planet approach to this migrating planet, then cross scattering occurs. So if the evaluated eccentricity is larger than unity, ejection occurs. So our model already included this model. So then, maybe I need to go. Yeah. So because this model, this migration model, often occurs in the inner region. So for the small mass planet, this migration ejection is dominated. So on the other hand, instability is mostly inward. Ejection of the small mass planet is often occurs. In the case of the orbital instability, already people know this process. In a model, we follow this prescription. First, find a multiple giant planets with 3 or more. Then estimate the instability timescale using some fitting formula and apply some analytical Monte Carlo model for cross scattering. For example, in this case, it compared with our prediction, Monte Carlo simulation, and this is n-body simulation. So our model will reproduce an n-body simulation. We also include the secular perturbation. When the orbit crossing between the giant planet occurs, then the secular perturbation is strong because the secular perturbation is proportional to the eccentricity of the perturbers. So there's some planet secularly eccentricity excited and they start orbit crossing with the giant planet and they ejected. And some other guys orbital eccentricity excited, but semi-axis is almost same. Yeah, because it is secular perturbation. So some of them are hit the host star. We also included this process. So then I want to discuss about the inconsistency with the orbital arm observation. So apparently our model underestimates the low mass ejected planet. In particular, around the M dwarfs case, underestimate. So this is huge underestimate. So for the instability model, I found that 9% of the system, this is a G-type star case, sorry. 9% of the systems, that kind of instability occurs. But this occurrence rate is consistent with the observed eccentric band gas giant. So it should be, it's not so, maybe okay. But I found the migration ejection occurs only in the 7.5%. So I mean very often shepherding occurs, not the ejection. So it could be too low. Recently, a new simulation, 3D global high resolution hydro simulation, including the disk planet gravitational interaction and accretion onto the planet. Lee et al. They did it, and they found that a very interesting result for Saturn to Jupiter mass planet. Type 2 migrations actually outward if the gas accretion onto the planet is included. So that if this happens, this is very for me. This result is very robust. in that case, migration can be outward. Then if the planet migrate outward, then the many planets there, then they're ejected. This process, this mechanism maybe increase the migration scat injection. So there are other models, maybe Yuji Matsumoto talked about that, and then more data from Roman. Then in that case, I think the free floating planet, if it is ejected planet, it constrains the migration and orbital instability in the planet formation. Okay, thank you.
Thank you so much. It's a great talk. Do you have any questions?
Thank you, Ina-san. Could you explain why I just read another paper, they have our migration, if they include the gas application of the planet?
So in this range, Saturn or Jupiter mass planet, disk is not so clear, clear enough. So there's still gas comes, and the most of the gas flow through the disk is actually accreted onto the planet. So the asymmetry between the inner disk and outer disk happens. Then due to the like a co-rotation torque, planet migrate outward. Yeah, for me, it is very reasonable.
Questions? Yeah.
May I ask a question about the red line, the instability model? So if instability occurred in a planetary system, you would expect a huge fraction of planets would get ejected by the dominant planet, the Jupiter.
Yeah.
So in this case, the mass function of ejected planet would just be whatever mass function you use for the whole system. So the fact that you observed a flat line, is this just the fact like you initialize the planets as a flat mass function?
Initialize, what do you mean? I calculate the mass distribution of planet from the planetesimal. So sorry, I didn't catch your point.
Oh, so you mean you run the simulation from the planetesimal stage?
Yeah.
Instead of assume a.
I don't assume any
I
I just start from this small planet and it grow and start gas accretion, become gas giant or something. Then each time step, I check the stability using the fitting formula. If this configuration, then the orbit crossing start or something.
Any final questions? Okay.
Smithson?
Not
Smithson. Sorry.
And I'm curious about in your simulation with the 3 Jupiter planets, in most of the cases, only one planet is get ejected or two.
Yeah, mostly one planet.
3.
Yeah, because if the one planet is ejected, then the other two guys are separated. Okay. Then after that, no more orbit crossing. Usually, but sometimes secure perturbation or something, they start again. But it is consistent with the n-body simulation.
I see. And for these two survived planets, do they have very abnormal eccentricity or they be circular?
No, of course, they are very eccentric. Usually, yeah.
Because I can expect after they skate outward or inward, they could have a very abnormal eccentricity, maybe which can be confirmed. But if we observe the system, that planet has very weird eccentric, abnormal eccentric, maybe it may indicate they underwent the tangent scatter.
Oh yeah, so actually radio velocity survey show that beyond 1 AU there are so many giant planet in eccentric orbit. So it is one idea to explain that kind of eccentric.
Thank you.
Yeah.
Final question from Sumi-san.
So your final plot of the distribution of the simulation, there seems the very wide separate planets is very rare. So our observation is the length maybe the either free floating or very wide binaries. What's which is abundant in your simulation, the free floating or very wide binary?
Oh yeah, it sort of depends on the perturber's mass. If the perturber is a Jupiter mass planet, then the gravity is so strong and mostly ejection. But in the case of the Neptune-sized planet, it's marginal, so they create the wide orbit planet or ejected. It's very marginal.